Okay, welcome back. So let's kind of do a little review from what we ended on last time. So we're looking at the justification for the transformation between ds and dA. So we had a little bit of a setup where we had some area underneath our surface. Something like this. And we had some vectors, u and v. And then we had the direction that we were projecting in, this p vector. And then finally, we also have some vector that's the gradient of g. So last time, we were able to write down that the area was the surface area times cosine of gamma k. And we said gamma k was the angle between this vector here and p. So what is this thing, right? Last time we kind of just arbitrarily drew one. Well, let's dive more into what this thing is. So now UK and VK make a plane that's based off of the function g, right? So now this is a level surface based off of g, and we know that the normal to that should be the gradient of g, right? Well, this is some vector in the plane and some vector in the plane, and then we're taking this cross product. So this is proportional to the gradient of g. So the angle is really the angle between this p vector and the angle between the gradient of g. So we can use that. Using dot product rules, this is the magnitude of the gradient times the magnitude of the p vector times magnitude of the angle. We'll keep red and y. Now my gammas look funny. The magnitude of the angle, the cosine of the angle between them. So this is the thing we want, this magnitude of cosine gamma. So we could write this as now this we're always going to be we're choosing to be a unit vector. So this will just be 1. So all we need to do is just divide this thing over. Like so. And then we can take this and plug it back into our expression here. Now the thing is we have this delta sk and we want to write it in terms of things that we can calculate. So we'll actually divide over this cosine, meaning that we look at the reciprocal. So we finally end up with the result that the surface area can be written in terms of the area, some small area, with this transformation factor here, like this Jacobian. Okay. So, and of course, once we take smaller and smaller surface areas, this doesn't become an approximation. This actually approaches the integral that we looked at before, which means that we finally have that the surface area integral is the area integral over the projection of that surface down to some coordinate plane. Oop, we forgot our f. Like so. And that's what we saw from last time. This is what we've been using. Okay, so let's get some more practice. Let's do some more examples. Let's get back into the swing of it. Okay, this time we're going to find the mass of the surface created by the cylinder x squared plus y squared equals 3, x squared plus y squared less than 3 in the xy plane. And the plane z is equal to 4 minus y. With surface density we'll call delta y squared plus z. Okay, so let's take a look at what this object looks like. So it looks like we first have this object in the xy plane, which is just a circle of radius 3. And then we have the cylinder here that kind of comes up and it ends up stopping when we get to some plane. So maybe we can, I don't know if I can rotate these. I don't think so. So we'll have to try doing some freehand. So eventually we hit some plane. Maybe something like this. And then so our object kind of looks like this. And what we're going to do is there are 3 sides to this object, right, that create this surface. And I can't describe all of them with a single expression. So I'm going to have to do these. I have to do 3 different surface area integrals to calculate the full mass. So I'm going to first say that the side is surface number 1. I'm going to say that the top is surface number 2. And then finally, I'll say that the bottom is surface area number 3. Of course, this is in our x, y, z. Okay. So now that we're going to break these up, let's start with S3. S3 is actually going to be pretty easy for us to do, and you'll kind of see why in a second. Maybe you can already guess. So for S3, we're on the xy plane. So what is our g function? We'll call this G3. It's a function of x, y, and z. Well, the thing that denotes this plane is z equals 0. That's a perfect candidate for our g function here. Right? This z equals 0 is the xy plane. And remember, the g function doesn't say where the bounds are, so don't get confused by that. It just merely says what is the behavior of the surface, not what the boundary is. The projection will handle that. So, step 1. This is already in the xy plane, and it's going to end up just being exactly what it is as a surface area integral for an area integral, but let's do the machinery and see why. So if this is already in the xy plane, let's project in the z direction, right? Let's project to the xy plane. So P will be k hat. The projection of course is itself in the xy plane. And this has a radius of √3. And again, I'm going to write off to the side here, maybe polar. This looks like a perfect candidate for doing polar coordinates. Step 3, I'm going to go ahead and calculate my gradient. So the gradient of g is 0, 0, 1. We should also say this is for G3. The magnitude of this gradient is therefore just 1. And when we take the dot product with k and we take it in magnitude, we just get 1. So the translation from ds to dA is just 1 dA. And that makes a lot of sense, right? Because this is just a flat thing. So we can just do the area integral of it rather than the surface area integral. It doesn't have any kind of alterations from just a normal area. So the one thing that we do have to keep in mind, though, is the thing that we're trying to calculate we're trying to find the mass on this surface so we need some density function here. So we actually have an integrand. So if we scroll back up, we've said that our integrand was this y² plus z, right? So here we've got y² plus z. Okay. But there seems to be kind of a problem with this, because if I am projecting to the xy plane, I have this z in here, and if I'm integrating with respect to x and y, I can't really have that z. But what we can do is use our g function. So remember, our g function here was that z is equal to 0. So here is the relationship that we want to use. So what we do is convert our density function, which was y² plus z. This is now just y², because we just substitute in z is equal to 0. We're also potentially interested in trying to do this in polar coordinates. So y squared is r squared sine squared of theta, just to kind of keep our options open. So now for step 5, we can actually go ahead and write this out. So M3 is our surface area integral, but we're now going to write this as our area integral. Now, the conversion from ds to dA is this magnitude of the gradient, or just 1, and then the magnitude of the dot product here over 1. So it looks like the conversion is just 1 to dA. We're actually going to do this in polar coordinates. So we're going to do an r squared sine squared of theta r dr d theta. Our r goes from 0 to root 3, and theta goes from 0 to 2 pi. Okay. So this is the integral from 0 to 2 pi of sine squared theta r to the 4th over 4, r equals 0, r equals root 3, d theta. We end up with 9/4, the integral from 0 to 2 pi. And now I have to do the sine squared d theta integral. Well, again, I can use the double angle formula here to help me out. So this is 1 minus cosine of 2 theta over 2 d theta. So we get 9/4, then theta over 2 minus sine of 2, not z, to theta over 4. Theta equals 0 and theta equals 2 pi. This just ends up giving us 9/4 pi. All right, so that was just the bottom surface, right? And it kind of introduced us to, now we actually had an integrand that we needed to use step 4 on. Right, we needed to kind of substitute out a variable there. Okay, so now let's keep going. Next, let's do the top, so S2. So for S2, the behavior of the surface is given by the plane equation. So our g function for G2 should be z plus y is equal to 4, right? So we always need a constant on this right-hand side. Okay, step 1. Why don't we also again project to the xy plane? So we'll let P be k hat. For step 2, the projection, this actually ends up being the exact same projection from S3. Because it's right on top of it. So again, this is an x squared plus y squared is equal to 3. This is the governing portion of this little circle here. So we have a circle of radius 3. So now for step 3, we look at our gradient. So we have 0, 1, 1. Where the magnitude of this is root 2. The magnitude of the dot product of our gradient with k hat is 1. Okay, so it's not just 1. We just have a relationship here with this root 2 now. For step 4, if we're projecting to the xy plane, we need the integrand to be in terms of just x and y. So again, we have to eliminate that z using our g function. So remove z. So we had that delta, this density function, was y squared plus z. Well, using our g expression, we can write this as y squared plus 4 minus y. So because our projection is a circle, again, I might be considering using polar coordinates. So I'm going to go ahead and just kind of preemptively transform this. So we get a 4 plus an r squared sine squared of theta minus an r sine theta. Okay, step 5. So our mass now, I am going to in fact use polar coordinates. So our surface area integral gets transformed to our area integral. We're going from 0 to 2 pi and 0 to root 3 in polar coordinates. Our transformation from ds to dA is this magnitude of the gradient, this root 2 over the magnitude of this dot product, which is just 1. So we'll just end up with a root 2 out here in front. So root 2. And then we had a 4 plus r squared sine squared theta minus an r sine theta r dr d theta. What did I see. So I was a little bit clever here because we already did this portion of the integral for m3. So we write this as root 2 m3 and then root 2 the integral from 0 to 2 pi 0 to root 3 of what was left over, which was just 4 minus r sine theta, r dr d theta. All right, because we already did this integral just above. So let's just keep going here. So we can substitute in what we found. This was 9/4 pi. Then we have root 2, the integral from 0 to 2 pi, 2r squared minus r cubed over 3 sine theta at r equals 0 and r equals root 3 d theta. Still have our root, still have our root 2, 9/4 pi plus root 2, the integral from 0 to 2 pi, 6 minus root 3 sine theta d theta. Root 2, 9/4 pi plus root 2 times 6 theta minus the square root of 3 cosine theta of theta equals 0, theta equals 2 pi, and we end up with 57 pi over 4. Oh, and we have a root 2 on the outside there. Okay. Phew. All right. That was our top side. So now finally, let's do the outside of this. Now, I am going to just scroll up a little bit here and kind of explain why this is actually pretty difficult. So let's scroll all the way back up to our image here. Where do you project this? Do we project to the XY plane? We can't, because what ends up happening is if we have this very vertical like surface area and we project down to the XY plane, it is the perimeter of the circle. It doesn't create this area. So we can't actually, in fact, do this that way. There's a few little neat tricks we can do. We could actually do this as a line integral, but where we try to find out how much mass is in every column and then follow this path around and then add up all of that mass. We could slice this cylinder in half and then project and do them separately. We could look at the projection onto like the left side onto the YZ plane, and then from the right side onto the YZ plane, or vice versa with the XZ plane. But that's still 2 more sets of surfaces that I need to consider, right? There's a clever twist that we can do. We can still do a surface area integral, but instead of projecting to a coordinate plane in the Cartesian coordinate system, what we could do is project to a coordinate plane in the cylindrical coordinate system. So instead, we're going to project to a totally different, instead of just doing Cartesian, we're going to do cylindrical. And in fact, why don't we actually start working out what would happen if we projected to the YZ plane, and then see why it would be pretty substantially difficult. And then we'll talk about how we do it in cylindrical instead. Okay. So you could do it this way. So where do I have where we start? Here we go. So if I wanted to project to the YZ plane, first off, this is our S1. We would have to let our surface, right? This is this x squared plus y squared is equal to 3. So this could be our candidate for our g function here. Unfortunately, we can't really do this, because if we have to consider the left and the right hand side separately, we can't consider them at both. So instead, if we want to split it up, we would have to say that x equals plus or minus y squared, 3 minus y squared, like this. And then we can treat each one separately. So our g function for one half of it would have to be x minus, we'll choose the positive here, and we have to move it over, 3 minus y squared is equal to 0. And then we would need a plus there for when we were trying to do the surface on the other side. So you can already see why this is starting to get difficult. We can't even consider this nice form here. We have to do 2 different separate cases and project each half to the YZ plane. So if we're going to the YZ plane, we're going in the X direction. So our P vector is I hat. Two, the projection looks like the side of our cylinder kind of projected to the YZ plane. And we have our plane. So we have our base, which is just Z equals 0. And then we have our plane on top that slices the top of the cylinder like this. And then we have the sides of the cylinder. So this is what the projection looks like. We know that this goes out to -√3 and √3 because it's a circle of radius √3 on the bottom. This goes up to a point 4 minus √3. This goes up to a point 4 plus √3 because this is Z is equal to 4 minus Y. Okay. For step 3, we'll say that this is G plus because we chose the positive version. So we can kind of actually retroactively put our little plus here. So the gradient of G plus ends up being 1 y over y squared minus 3, 0, which means that the magnitude of this guy is 1 plus y squared over R3. Oh, maybe I have this reversed. I think this should be 3 minus, nope, keep writing it like that. Let's just use the eraser tool. Nope. Still no. Okay, there we go. Okay, so already, this is just the numerator of our translation here. Yes, the question is, why don't we use symmetry to calculate mass for this? Because the density isn't uniform. So now that we have the magnitude of this guy, at least the magnitude of this dotted with I hat is equal to 1, right? Because then we just pick up this 1 here. But this integral gets kind of gross, right? But this is just the numerator here. And I still have my y squared plus z that I have to remove. No, actually with y squared plus z, we'd be fine. We would have to remove any x's because we're projecting to the yz plane. So I'm gonna stop here. You could continue if you want, but this isn't the best or the cleverest way to kind of doing this surface area. Instead, So let's put a big stop. This is bad. I don't like this. So instead, let's say that our g function is rather a function of r, theta, and z. And then when we have x squared plus y squared, we can really say that this is r squared, and this was equal to 3. So now we don't have to worry about cutting the cylinder in half, and you'll see why. So for step 1, if we project onto the theta z plane, we let P go in the r hat direction. Okay, right? If we're going to the theta z, then we have to go in the r direction. Well, what the heck is the r direction? So let's take a look. How do we express r hat in terms of I hat and j hat? Well, it certainly exists in the xy plane. And it's some vector that comes out from the origin, and it's a unit vector, and it just comes out this, right? So here, in this direction, we have I hat, and in this direction, we have j hat. And there's some angle, right? Some angle theta. So in fact, when r hat points like this, theta hat points in the direction that theta is currently pointing in, and then z is just in the normal direction. So because this is a unit vector, it has a x component of cosine of theta. It has a y component of sine of theta. And it has a z component of 0. And you can check that that, in fact, is a unit vector. Okay. So now, what does this projection even look like? Right? If we're projecting to the theta z plane, how do I kind of visualize this? So imagine for a second that r theta c in a Cartesian plane. We know that r is root 3, right? Just from our function above, right? We said that r squared was equal to 3. So now this is just a way for us to kind of think about what this looks like. So here we'll have a theta, r, and z coordinate system, kind of like Cartesian. So at r equals root 3, I have my function here. And for any given theta, I draw its corresponding z value. Well, for going from 0 to 2 pi, the bottom of it stays flat. However, the top of it goes like some plane, right? The top of it goes like z, straight line, z is equal to 4 minus y, which we could rewrite as 4 minus r sine theta, which is, now this r we know is a constant value. This is 4 minus root 3 sine theta. So it looks like we have maybe some kind of sine function here as the top of this curve, right? So this is what it looks like in this Cartesian setup of cylindrical coordinates. So if I wanted to think about what the projection of this object looks like onto the z theta plane, we're disconnected there for a second. We can actually draw out this projection here onto the theta z plane. And we want to do one full revolution, so we'll go from 0 to 2 pi. And we have the equation z is equal to 4 minus root 3 sine theta. So it looks something like that. So that's what our projection looks like onto this theta z plane. Okay. If that's what the projection looks like, let's move on. The gradient of my g function. So remember our g function, so let's kind of write here. G1 was x squared plus y squared is equal to 3. So we can take the gradient in Cartesian coordinates. Otherwise, we get 2x, 2y, and 0. But then we need to convert this into our cylindrical form. So 2r cosine theta, 2r sine theta, and 0. So the magnitude of this here is the square root of 4r squared cosine squared theta plus 4r squared sine squared theta, which is equal to 2r. And don't worry, we're going to deal with this r in a second. So now the dot product of this function, or sorry, this gradient with r hat. So remember, r hat was cosine theta sine theta. So we end up with the absolute value of 2r cosine squared theta plus 2r sine squared theta, which is just 2r. Oh, so it looks like these end up canceling, which makes sense because this is what the object looks like in this Cartesian setup, and it's a flat surface over here. So when we project it, it's still a flat surface, so the conversion should end up just being 1, right? Because this is our numerator and this is our denominator. So now for step 4, since r is root 3, we take a look at our density function, which is y squared plus z. We can write this therefore as, because this is r squared sine squared, this is 3 sine squared theta plus z. And then finally, we can integrate. So our mass is 0 to 2 pi, 0 to 4 minus root 3 sine theta. Then we have 3 sine squared theta plus z. Now, we still need this r for cylindrical coordinates, but that ends up just being root 3 because of our constraint function here. So we still have a Jacobian, that extra r, but because we're doing dz d theta, we need to replace that r with this root 3 here. Or we go from 0 to 2 pi. Let's bring out that root 3. Then here we have 3 sine squared theta. Oh, oh yeah, we're doing the z integral first. So this just means that we have a 4 minus root 3 sine theta plus 1/2 of 4 minus root 3 sine theta squared d theta. Bring that root 3 outside. Integral from 0 to 2 pi. The quantity 8 minus 4 root 3 sine theta plus 27 over 2 sine squared theta minus a 3 root 3 sine cubed of theta d theta. Okay, I'm not actually going to do out the theta integral. You would have to use double angle here, and you could actually do another double angle here, or some trig substitution. But the end result, 59 root 3 over 2 times pi. So then for our total mass, all we need to do is just add up our M1, M2, and M3 quantities. Okay, so this is a hard problem. I don't really expect you guys to be able to do a projection onto a different coordinate plane than the Cartesians. So most of the time, I'm assuming that you guys can do an X, Y, or Z direction for your projection. I just wanted you to see that this concept still exists for different coordinate systems and to kind of get an idea of, okay, if I wanted to do a different coordinate system, what's the kind of procedure behind that? What does r hat look like? What does theta hat look like? What directions are they in? You can just use knowledge that you know about the Cartesian differences and like their geometric relationship with cylindrical, or you can even think about doing spherical. Is the process sorry about that. Is the process for choosing which plane to project the easiest shape to integrate? Yeah, I would definitely assume that the shape of the projection is a large factor and what I would consider where I'm projecting to. Right. Okay, why don't we take our 5-minute break here, and then we'll come back and we'll start talking about vector surface integrals. All right, let's get started again. So now let's start talking about flux through a surface. So we've already talked about flux through a line. Now let's talk about flux through a surface. So maybe you have some running water, and it pours through some spigot or some faucet, and you know the surface area that it's coming through. What is the flux or like rate of this water going through this particular surface here? So before we jump into it, let's look at a definition. A smooth surface S is orientable or two-sided if it is possible to define an outward pointing unit vector or unit normal n that varies continuously with position. So it's just a math way of phrasing that an object has, a top or a bottom, right? So it's not that you can construct some shape that can't really exist in the real world. So let's kind of figure out if we have a vector field that goes through some surface. So kind of let's start by imagining now a fluid velocity field written as a vector field F, which has component functions P of x, y, z, Q of x, y, z, and R as x, y, z. This gives the fluid's velocity at any given point. So the question is, what is the flux or rate of flow through any given two-sided surface? So how do I even start trying to figure out what this looks like? Well, again, let's use the ideas that we've kind of learned about for surface areas to help us get there. So as always, we're going to break down our domain to approximate, right? That's what we've been doing all the time with these integrals, is do a small approximation, and then in the limit, we get the integrals that we desire. So some small segment of surface area is the thing that we're going to be considering here. So imagine we've got maybe some small little segment of some surface area, some ds little strip. We have a few things to consider. We have the vector field that is coming through the surface, and then at any given point, we also have the normal vector. So if you zoom in close enough, make your ds small enough, the amount of fluid that's going through this surface is the amount in the n direction. So the amount of fluid going through this surface is the amount in the n direction. So if we summed up all of these little small surface areas with the amount that's going through each little particular thing, you get an approximation if we sum those up, and in the limit, we end up with the flux. So the flux through our surface is the surface area integral over S of how much of F is going in the n direction, which is the dot product between the two, ds. So just like line integrals, there is a shorthand that goes with the vector form. You'll typically see this written as f dot ds as a vector. These are just equivalent things. This is just a shorthand for it. This basically just groups the n vector with the small surface area differential. Okay, so now how do I actually do this out? How do I find this normal vector? How do I start doing this dot product? Well, the normal vector can be defined as, so we're actually going to use it as a unit vector. And if we have, imagine that at any given point on the surface, you found the tangent plane at that point. They both have the same normal vector, meaning that if I look at the gradient of the function g that defines this surface, then this is either plus or minus the gradient of g, and we need to make it a unit vector. So we have over the magnitude of the gradient of g. So now, where does this plus or minus come in? So this is exactly because the surface is two-sided. We have to define our n hat in the direction that we consider outward, meaning where is the surface going through, right? So in this case, I wanted to know how much fluid was coming out in this direction, right? If you imagine I had my n in the other direction, if I said this is the bottom of this shape is my outside, then I would get the negative answer for my flux, which makes sense, right? I have fluid that's going the opposite direction of n, so I should expect a negative answer there, right? I have fluid going this way, not the other way, per the illustration. So we'll kind of get into how we choose the plus or minus given our given surface in a few examples. But let's move forward. In the general case, we'll just write it like this. So we can go ahead and plug that into our flux. This is over a surface S of F dotted with plus or minus grad G over the magnitude of grad G ds. Now, this is a surface area integral, and we just talked about how we translate these by projections. We know how to calculate surface area integrals now. So this will equal our area integral over the projection R of F dotted with plus or minus grad G over the magnitude of grad G. And our ds to dA is the magnitude of grad G over the absolute value of grad G dotted with the direction that we're projecting in, this P vector, dA. Well, now the denominator here and the numerator here end up canceling. So we can write this as the area integral over R of F dotted with plus or minus grad G 1 over the magnitude of grad G dotted with P dA. So it's not that much more complicated than doing a normal surface area integral. We just have to calculate this dot product, right? We don't even really need to worry about the magnitude of grad G anymore. We just need grad G. Okay, so let's do an example. We're going to find the flux through the surface given by y is equal to x squared plus z squared, where y ranges from 0 to 1. And the disk x squared plus z squared is less than or equal to 1 at y is equal to 1. Of the field, F is the vector 0, y, negative z. Assuming out is positive. Okay. So this surface seems to have two very distinct faces, right? So let's kind of just do a sketch of what's going on here. We have some disk at y is equal to 1, where x squared plus z squared is less than or equal to 1. So it includes this entire little disk here. And then we have this paraboloid, y is equal to x squared plus y squared from 0 to 1. Ooh, don't want a straight line. So something like this. So it's like a bowl that we put a cap on. Just, rotate it. Since this is our x, y, and z. So we'll call this part S1, and we'll call the flat part here S2. And out is positive, so any unit normal vector should be pointed out of this object, not into the interior. So here's some examples of our normal vectors. Now let's figure out the flux through each of these surfaces individually, because there's no way for us to do one surface area integral because they don't really share a common g function that we can utilize. So let's start with S1. For S1, our function is y minus x squared minus z squared is equal to 0. Step 1, we need to choose a direction to project to. We're not going to choose the xy plane, because what would happen is if we project to the xy plane, we have half of it above and half of it below the xy plane. So if we do that projection, we kind of double up. Perhaps you could use symmetry, but it is also pretty easy to just project to the xz plane. In the xz plane, the projection here just looks like a circle. So we can go ahead and project to the xz plane. The projection here, like I said, is just a circle. This ends up just being a circle of radius 1. And again, this is maybe a consideration for polar. So this is the xz plane. So maybe polar. Where x is equal to r cosine theta and z is equal to r sine theta. So for step 3, we look at the gradient. We end up with minus 2x, 1, and negative 2z. Let's actually go ahead and also calculate the dot product in magnitude. We chose j hat. Let's go ahead and put a j hat there. This is our y component. and we're just taking the absolute value, so we end up with 1. Okay, so now as an augment to doing a normal surface area integral, step 3 will also now include that plus or minus, right? So we need either plus or minus this grad g. So which one is it? Which one is it going to be? So remember, this is detailing what our normal looks like, right? Where is our normal pointed? Okay, so if our normal, remember back from our little plot up here, is pointed outside of this, right? So if you think about any vector that's pointed on the outside of this, it's always going to have a negative y component because this paraboloid never gets completely parallel with the y-axis, right? It gets steeper and steeper and steeper, but it never gets exactly parallel with it. So that means that any vector is just pointed somewhat in the negative y direction. So if I take a look at my gradient here, I need this to be pointed in the negative y direction. But as it stands, it's pointed in the positive y direction. So if I chose the negative, I could rectify that. So we end up choosing the negative version. So we choose the negative of the gradient. At the same time, I'll go ahead and actually calculate this dot product. So f dot minus grad g. This is our vector field was 0, y, negative z. We're dotting this with a negative. So 2x minus 1 to z. This ends up giving us negative y minus 2z squared. Step 4. We're in the xz plane, so we need to get rid of any y's that show up in our integrand. Well, this is what our integrand is going to look like, right? This is f dot grad g, or negative grad g. So I need to remove this y. Oop. There we go. And remember that our function g x, y, z was that y minus x squared. Oh, I didn't leave myself enough room. I'll just say that y says that y, or g provides us that y is equal to x squared plus z squared. So I can go ahead and substitute that in. I can get negative x squared minus 3y squared. Sorry, z squared. All over the place today. All right, step 5. This seems like a pretty good candidate for trying to do polar coordinates. So the flux for surface 1 will end up being the area integral of f dotted with negative grad g over grad g dotted with j hat dA. So we can translate our dot product here into polar coordinates. We have this negative that comes out. These are both negatives here. So I'll have negative the integral from 0 to 2 pi, and we have a radius of 1 for our projections. We go from 0 to 1. And then x squared becomes an r squared cosine squared theta. And then our z squared becomes a r squared sine squared of theta. And then we have an r dr d theta. So we can do this integral out. This is negative the integral from 0 to 2 pi. Why does that become a plus? Are you talking about the plus here? Okay, never mind. Okay, you got it. So we have 0 to 2 pi. And then we're integrating over r. We have cosine squared theta plus 3 sine squared theta. We have an r to the 4th over 4, evaluated at r equals 0 and r equals 1, d theta. Integral from 0 to 2 pi, 1/4. And then what we can do here is there's a cosine squared here. There's 3 sine squared here. So what I can do is take one of the sine squareds and have that equal to 1. But then I'm left over with a 2 sine squared theta, b theta. So I can use a double angle formula for the sine squared here. Negative 0 to 2 pi, 1/4. Let's finish that 4. 1 plus 2 times 1 minus cosine 2 theta over 2 d theta, or negative the integral from 0 to 2 pi, 1/4 2 minus cosine 2 theta d theta. We have a negative 1/4 2 theta minus 1/2 sine of 2 theta. Theta equals 0 and theta equals 2 pi. This just gives us negative pi. Okay, so it looks like the flux is this negative pi, meaning that the direction, or like there's a net flux that is going into the interior of this particular surface. So we know which kind of way this like the fluid flow is going here. So that was only S1. So let's go ahead and do S2. The function here was that this is located at y equals 1. So we can use that. That's the behavior of the surface. For step 1, let's again project to the x, z plane. So we get j hat. 2, this is the same projection. So again, maybe we use polar. We can use the same setup as we did before, where we have x being r cosine theta and z being r sine theta. For step 3, the gradient here is 0, 1, 0. The magnitude of the dot product, oh, let's put j hat in there. This ends up just giving us 1. So this time out, if we scroll all the way back up to our surface, all the way back up here, this time the normal should be pointed in the y direction, right? This is a flat surface, and we're trying to point in the positive y direction. So you could have even just guessed what n was. It is just going to be a unit vector in the y direction. But we need to say that we're choosing the positive here because we want this to have a positive y direction. It's pointed out of this object. So we choose the positive. So when we do our dot product, we choose the positive version of g. So we get 0, y, negative z, dotted with 0, 1, and 0. This ends up just giving us y. So we're projecting to the xz plane. So we can't have any y's in our integrand, so we actually have to get rid of this. But we know that given our function g, that y is just equal to 1. So we remove y, which is to say that the dot product is just 1. So the flux for the second surface is therefore the area integral over the projection of f dotted the positive version of grad 2 or g2 dA. Okay, so we know that this dot product gave us 1. The magnitude here was just 1. So what ends up happening is that this is just the area integral over the region R of dA. So we could do this out. We could do this in polar coordinates. From 0 to 2 pi, 0 to 1 of R dr d theta. Could do that. But we also know that this just means the area of the region R, which in this case, the projection was just this circle of radius 1, which meant that we have pi. So the total flux is the flux of both of these put together, which was negative pi and now pi, which means that the net flux through this object is equal to 0. So that means that just as much is leaving as that is entering this object. It's really cool. We're going to be learning a little bit about how to do these calculations for closed surfaces a lot quicker. That's going to be another big theorem that we're going to have. But for now, why don't we call that a day? We have about 5 minutes left, but we have one more example that I want to go through for surface area stuff that we can continue on Monday. Oh, we have another question. So let me go ahead. I can stop the recording now.